7043. Our group will be presenting on thorium and its application as a nuclear fuel source. My name is Sam Smith, and I'll open the presentation with a brief history on nuclear science and discovery of radioactivity. Hussein Al-Matar will present a section on the dawn of the nuclear age, and Perry Eddy will wrap up with a section on power and politics and do a comparison of facts on uranium versus thorium as a nuclear fuel source. The first slide, you can see these are the pioneers of radioactivity. On the left there you have Henry Becquerel, who was a French scientist who in the year 1896 conducted an experiment which started with the exposure of a uranium-bearing crystal to sunlight. Once the crystal sat out in the sunshine for a while, he placed it on a photographic plate. As he anticipated, the crystal produced its image on the plate. Becquerel theorized that the absorbed energy of the sun was being released by uranium in the form of X-rays. He did not further pursue research, but in turn sort of passed the torch on to couple that are known to be the main pioneers in the invention of radioactivity, Marie Curie and Pierre Curie, who are a husband and wife team that experimented with their own uranium-containing ore. They came up with the term radioactivity to describe spontaneous emissions that they had studied. While comparing the activity of pure uranium to a uranium ore sample, they found that the ore was significantly more radioactive than the pure material. They concluded that the ore contained additional radioactive components besides the uranium, this observation leading to the discovery of two new radioactive elements, which they named polonium and radium. For this work, Becquerel and the Curies received the Nobel Prize in Physics in 1903, and Marie Curie further on received another Nobel Prize in 1911, the first woman at that time to receive a Nobel Prize and only person at that time to receive multiple Nobel Prizes. Here's a quote: "Marie Curie's notebooks are still too radioactive to be handled without protection. They will continue to be held until at least the year 3511. The unit today to measure radioactivity is the Curie, so they were huge and implemental, the godfathers of radioactivity. Moving on to the second slide, as you can see, those are basically the periodic table of elements, which I'm sure we all saw in chemistry class when we were kids. This outlines all the different radioactive elements. They're naturally occurring elements which are concentrated between the atomic numbers 84 and 118 on the periodic table. Interestingly, there is a break between the numbers 110 and 118 on the table, which are suspected radioactive elements which have not yet been discovered. To date, scientists have discovered 29 radioactive elements, all of which are named on the periodic table. The next slide briefly outlines nuclear science and its application to World War II and the race for the bomb. And it all started in Germany in 1939 when German chemists Otto Hahn and Fritz Strassmann published the results of their experiment in which they bombarded uranium with neutrons, neutrally charged particles, and they found barium, an element roughly half the size of uranium. Their former colleague Lise Meitner, who a few months after had been forced to flee Germany and seek refuge in Sweden, and her nephew Otto Fritsch realized that the uranium nucleus had split into two. These revelations touched off a frenzy of scientific work in fission around the world. The German uranium project began in earnest shortly after Germany's invasion of Poland in September 1939, when German Army Ordnance established a research program led by the Army physicist Kurt Diebner, bottom left, to investigate the military applications of fission. By the end of the year, the physicist Werner Heisenberg to the right there is this picture, had calculated that nuclear fission chain reactions might be possible. When slowed down and controlled in a uranium machine or nuclear reactor, these chain reactions can generate energy. When uncontrolled, they would be a nuclear explosive many times more powerful than conventional explosives. As you can see there to the right, that's a nuclear pile at Hagerlock. Those are two pictures taken from there where scientists tested these nuclear developments. And on the top right there is not a prototype, but a design of the first, I guess, the Nazi atomic bomb, which there's no proof was ever used. As we know, the U.S. and Russia were the first two countries to use any type of nuclear bomb. No proof exists of Germans testing an atomic bomb, but the image to the right supports evidence that Germans definitely sought to develop a nuclear weapon and claim to have had tested a device near the end of World War II. Post-nuclear development in the USSR, the Soviet project to develop an atomic bomb effort was led by Igor Kurchatov in a secret site known as the Arsmas 16. Early efforts were greatly aided by spies inside the Manhattan Project, most notably Klaus Fuchs, who was a German scientist who also helped with U.S. efforts in the Manhattan Plan project. The Soviets began construction of a near copy of the Fat Man bomb using a detailed design provided by Fuchs. The replica, named Joe 1 by the West, was detonated at Semipalatinsk tests in Kazakhstan on August 29, 1949. After the war, the Soviet Union continued to expand its research facilities, military reactors, and employed many scientists. Greatly aided by its successful Soviet ALSOs and the atomic spy ring, the Soviet Union went on to conduct a series and test a series of nuclear bombs over the years to come. With the success of the first test, the Soviet Union became the second nation after the United States to detonate a nuclear device. I will now pass on to Hussein, who will talk about the U.S. efforts and development of nuclear in the Manhattan Project. Thank you.
Thank you, Sam, for the overview. My name is Hussein, and I'll talk more about the Manhattan Project. The German scientist has learned that the secret of splitting the uranium atoms, so the world feared the Nazi scientists could utilize the knowledge and produce bombs capable of unimaginable destructions. These scientists believed that if the German and Italian leaders could get a hold of the dangerous weapon, the planet could be a dangerous place to live. So, the Manhattan Project involved two scientists, Albert Einstein and Enrico Fermi. These two scientists advised American officials on the need to start an atomic research program. The idea would help counter atomic threats that might be posed by other countries, and the American government designed and built the atomic bomb coded name the Manhattan Project. So now I'll talk about the first bomb. And the name code for it was the little boy the atomic bomb was dropped on Hiroshima City. The bomb had 64 kilograms of enriched uranium. The effect of the little boy was fascinating. The bomb has a length of about 3 meters and a diameter of about 70 centimeters and weighed approximately 4.4 tons. The uranium meant to undergo nuclear fission were less than a kilogram of uranium transformed into different types of energy, heat, and radiation. The bomb killed about 80,000 people instantly. Other people died as a result of long-term effect, and the total death was estimated to be about 150,000 people. The next bomb that's been used was Nagasaki. The atomic bomb code name was the Fat Man. and was dropped over the city of Nagasaki on August 9, 1945. The bomb's length was about 3.3 meters long and 1.5 meters in diameter. The design of the bomb prompted the drafting of its code name. The death was estimated to be about 75,000 people. The death rate at Hiroshima was greater than the one at Nagasaki, since the city was located in a flat region. So next I'll talk a little bit about the Cold War. And basically the Cold War started at the end of the World War I. In the late 1940s, the Soviet Union detonated its first atomic bomb, and the result prompted the beginning of the arms race. So the Soviet Union atomic bomb activities sent shock waves to the US government and its allies. So in the 1960s, the US and the Soviet Union engaged in a political confrontations due to the Cuban Missiles Crisis, and the two countries resolved after agreeing that risking nuclear war would be too risky.
In the years of the Cold War, the USA developed several centers of excellence for the research and development of nuclear technologies and processes that supported the creation of nuclear applications. One such center of excellence was the Oak Ridge National Laboratory in Tennessee. At Oak Ridge, scientists and theorists delved even deeper into the promise of nuclear energy. Splitting of the atomic nucleus, known as fission, and the combination of two smaller nuclei into a larger one, known as fusion, were explored at great length to gather their secrets and to glean any technological edge that they might represent over the Soviet Union. The military initially had key interest in both types of nuclear reactions. Older atomic bombs used nuclear fission. However, these devices produced lower yield explosions than that of fusion devices, such as the hydrogen bomb. The hydrogen bomb is the precursor to today's nuclear device. Even as their knowledge of nuclear technology increased, both fission and fusion had their places in military plans. Due to its rapid release of energy, fission was the obvious choice for thermonuclear ordnance, and its effect was devastating. Due to a more controlled and controllable release of energy, fusion made much more sense for utilities and in the generation of electricity and steam. There are several radioactive substances used in the field of nuclear science, such as plutonium, barium, and radium, but there are two that are best suited for the generation of large-scale power. Those are uranium and thorium. Most people are aware of the power possessed by uranium, but many are unaware of the awesome power and abundance of thorium. In the 1940s and 1950s, at Oak Ridge National Laboratory, uranium was, and still is today, closely related with light water and heavy water reactions. During that same time, Oak Ridge science teams, under the direction of Dr. Alvin Weinberg, were studying and developing technology using thorium as a nuclear fuel. In the 1960s, Oak Ridge not only designed a thorium reactor, but it built and set one into stable operation. The new type of reactor used for thorium reactions was called a molten salt reactor, or MSR. More specifically, it was a liquefied fluoride thorium reactor, often called LFTR or lifter. Dr. Weinberg was equally involved in the development of systems that used uranium fuel and those that used thorium fuel. However, Weinberg quickly became a proponent of thorium-based technology. The early development of modern nuclear industry was formed in a passive-aggressive struggle of wills and intellect between Dr. Alvin Weinberg and Admiral Hyman Rickover. Rickover was an administrator with an authoritarian approach born out of naval tradition and discipline. He was also an academic that saw nuclear energy as the weapon that would make USA untouchable. Weinberg was an academic of good nature and an administrator that believed in teamwork. Weinberg's goals were to create a world where nuclear technology would be used for the peaceful betterment of humankind. The differences between these two men could not have been more dramatic, yet they were perhaps as close friends as two competing visionaries could be. For the decade after the end of World War II, the military-industrial complex, as it has become known, focused on the development of nuclear delivery systems. Missiles and bombers could deliver nuclear warheads to targets around the world, but airborne ordnance could be detected and possibly defended against. Admiral Rickover sought other means to use and deliver nuclear technology on the battlefield. Rickover envisioned a navy where submarines would be nuclear powered and at the same time would bristle with nuclear ordnance that could be launched from anywhere in the ocean. In Rickover's vision, a nuclear submarine would be able to travel at 26 to 30 knots, submerged for many years without resurfacing or refueling. In 1946, a pivotal meeting happened between Rickover and Weinberg, where the discussion turned to the type of reactor best suited for the propulsion of nuclear submarine. At that point, Rickover was supporting the use of a liquid fluoride thorium reactor. However, as Weinberg pointed out, there was a major problem of using liquid fluoride in a submarine, and that is, it explodes when in the presence of water. A light water uranium reactor was a better fit for a Navy that was designing a PhD level technology that had to be maintained by a high school level personnel. Admiral Rickover was often quoted as saying, the Navy has the best plumbers in the world, and water, unlike sodium, is something that the Navy ought to know about. As a result, the first real-world application of nuclear power generation was launched on board the Nautilus in 1954. It was not developed for the use of a commercial power plant, and it was not chosen because of its inherent safety or efficiency. It was selected because it was best suited for the objectives of naval deployment. For some reason back on shore, the mentality developed that if it was good enough for the Navy, it's good enough for America. So the government took the first steps towards a nuclear energy system for civil utilities. It had a bias towards uranium technology. This uranium bias was a logical reaction because the Navy veterans were already well trained in the operation of these systems, so they provided a ready source of operators for these nuclear plants. So nuclear power plants were built using light water uranium reactors, exactly the same as on the nuclear submarines that the operators had served on. Moving further down the road, many will remember the nuclear incident at the 3 Mile Island thermonuclear power plant in March of 1979. There was a partial meltdown of reactor 2, that's known as TMI-2, that resulted in a release of radioactive matter. Even though there was no loss of life, nor any measurable negative health effects, the 3 Mile Island incident at the time was considered to be a very serious incident, and it spawned major changes to the entire operation of the nuclear industry in the United States. In retrospect, we can see that the whole incident was relatively benign as compared with some of the events that have precipitated since that time. In 1986, disaster truly struck at Chernobyl nuclear facility in the former Soviet state of Ukraine. The combination of design factors and human error resulted in a steam explosion and fires, releasing radioactive gas and smoke into the atmosphere. 2 plant workers were killed immediately, and 28 others died of radiation poisoning within weeks of the event. Since the time of the accident, the area has seen an increase in the incidence of thyroid cancers linked to radioactive release. Then again, in March of 2011, nature conspired to expose the weakness of current nuclear power generation technology. A subsea earthquake off the Japanese coast spawned a tsunami surge toward Japan. The Fukushima Daiichi nuclear power plant stood strong against the earthquake, but was brought low by the tsunami waves that followed. Ironically, the waves caused a power outage at the power plant. As a result, the cooling system would not work, and all 3 reactor cores melted down. While there was no direct or indirect deaths reported as a result of the nuclear disaster, an unsurpassed volume of radioactive material was released into the air and ocean. Now I'd just like to briefly go over some of the pros and cons of using uranium fuel in light water reactors versus using molten salt reactors with thorium fuels. For uranium fuels in light water reactors, the pros consist of nearly 0 greenhouse gas emissions, relatively low operating costs, known developed technology, large power generating capacity. The cons are high construction costs for radiation containment, reliance on subsidies for construction and operation, high known risks in an accident when we deal with probability versus severity, long horizon construction cycles, targets for terrorism, corporate, government, and insurance liability issues. They require large infrastructure, usually found in populated areas. Uranium fuel preparation and utilization produces considerable environmental waste. Uranium is a non-renewable resource. Uranium fuel is expensive to mine, refine, and transport. Waste from uranium fuel lasts 200 to 500,000 years. There is a current lack for long-term waste storage or treatment. Shipping nuclear waste poses a threat of interception by terrorists or of accidental release. Only 5% of uranium fuel is used to produce useful energy. And high pressure operation. A lot of these reactors do operate at very high pressures, high temperatures, and are prone to failure. Pros and cons of a molten salt reactor using thorium fuel. Pros: nearly 0 greenhouse gas emissions, relatively low operating costs. Design has a natural fail-safe mechanism, large power generating capacity. Technology can be miniaturized to decentralized generation. Large infrastructure is not required. Thorium is more difficult to weaponize than uranium. 98% of thorium fuel potential can be harnessed as useful energy. molten salt reactors operate at low pressure. These reactors can produce more fuel than they consume when they operate on thorium fuel. They can also process nuclear waste from uranium reactors to make it benign or less harmful to the environment. It produces less power as heat increases, eliminating meltdown situations. So as the heat in the system increases, the power it produces decreases, and as a result it will shut itself down rather than melt down. It produces 1,000 times less waste by volume than uranium. Waste produced, 83% is safe within 10 years. The remaining 17% is safe within 300 years, as compared with thousands of years for uranium. The design is simpler than traditional light water reactors, and on a historical front, a 7.4 megawatt reactor of this type ran for 4 years at Oak Ridge National Laboratory from 65 to 69. The cons of this type of system: risks may be unknown due to lack of historical operating data and experience in adverse conditions. Initial facilities will have high construction costs. There will be a long horizon for approval to build commercial facilities of this type. They are still a target for terrorism. It is a non-renewable resource, however, thorium can be bred in a reactor. And in that case, it would create more fuel than what it uses. And it produces hazardous waste, just less. And there's a lack of long-term storage capacity for the waste it does produce. Overall, I think that based on the pros and cons, there is a case to be made for investigating molten salt reactors using thorium fuel. I hope that the people in power that have an opportunity to look at the energy future of North America and the world take the time to consider using thorium fuel for generation of electricity due to its inherent safer qualities. Thank you.